All right, so let's get started. I know that many of you are going to be in class going, yeah, Dr. Michelson's talking about stuff, and there's like this bolt stuff he's talking about, and we really don't care because there's a celebration coming up in a few minutes, right? Well, we press on in here. Damn it, we are moving on. All right, so that's what YouTube is for, right? I know there's a number of people who decided they're going to stay back and study. They're getting absences. That's just, it is what it is. It is what it is.
Hey, you better make sure you pass out that sign sheet, going around.
Right there. Hold on, wait. Marker drop.
Somebody get rid of these markers.
Hey, I got erasers. That's exactly it. Well, I use it for my bolt. It's my, my bolt that I shear. It's the bolt. Okay, real quick, if I had to wager, the majority of you haven't started homework 4, and I get it, but it is on the horizon. I'm going to go ahead and prepare you for something. So the plan is in here in steel design to have an exam before spring break. So here's the idea. Now, I know everybody's going, but there's a good side to it. Okay, I built in makeup days for the semester, and we haven't had a need to use them because we haven't had any snow days. So this is what I'm going to do. The plan is for the week before spring break, we have our exam review Monday, we have the exam Wednesday, no class on Friday. All right, is that all right? And we have an exam in steel design before spring break, but not one in concrete. The concrete exam isn't until after spring break. And we're not going to have class on that Friday before spring break in concrete design either. I think I'm a pretty reasonable guy, right? Thank you. But we are going to have an exam in here before spring break. I don't know. just say it outright, This is a microphone, by the way. It is recording. Oh, okay. Yeah, that's the difference between first and second degree. Okay, so... Oh, man. I do love this job. All right, so real quick, we do have that bolted connection homework due on Wednesday, so you do need to make sure you're at least aware of it. Our second exam will be on bolts and welds, all right? And in all honesty, it's actually one of the shortest periods of material on an exam. Like, there's actually not a lot on it. Traditionally, in steel design, my second exam is the easiest. So I want everybody to be aware of that. So, we have an exam before spring break, but it shouldn't be that difficult an exam. So I just keep in mind you've got that homework due on Wednesday, on March 1st. Class will end today 5 minutes early to prepare for the celebration in concrete. Okay, so today what we're going to do is we're going to finish bolts, and we're going to at least get started into welds, at least talking about it. Which is good because I know a lot of you are thinking about concrete. There's not going to be any heavy material we're going to discuss with welds. We're just going to finish this example, which is going to be pretty quick, and then get into welds. All right, sound good? All right, so let's just recap what we were looking at last time. So we finished slip critical, and then we were looking at combined loading scenarios. So in a combined loading scenario, the idea is I have a group of bolts that is seeing a combination of both shear and tension, okay? And when you analyze a connection that's seeing both shear and tension, we've got 3 checks we've got to make, essentially. We've got to check the shear capacity, the tensile capacity, and then both, the interaction between the two. Because if you've got both shear and tension, you're going to have a reduced capacity. Let's say if we're talking about shear, you're going to have a reduced shear capacity in the presence of all that tension. Or you can look at it the other way. You're going to have a reduced tensile capacity in the presence of all that shear. So we have to assess that interacted effect. So last time what we did is we started to look into analyzing the connection. And there was a couple points that I wanted to make that we didn't quite have time to do. So first off, here's the connection, and we have 1.2 times the dead plus 1.6 times the live, and we said, all right, that's 90 kips. Okay? Now we took that 90 kips and we split it up into X and Y components, or in this case, tension and shear. And we got a tensile component of 72 kips and a shear component of 54 kips. Everybody with me on that? Now, one of the things about this connection that I want to talk about are the forces. If you recall, I said that we really don't need to worry about interaction if the comparison between those two forces is less than 30%. In other words, if we had 72 kips in tension, but we only had 5 kips in shear, there's not enough of a shear to really affect that tensile capacity. Make sense? That's not really the case here. I mean, we got a significant tensile force and a significant shearing force, right? I mean, 72 kips and 54 kips, they're well within 30% of one another. So we have to check that, that interacted effect. Does that make sense? So I just want you to recognize that there's a lot of tension and a lot of shear, enough so that we actually have to go through and check both. All right. Sound good? All right. I'm going to erase this here, this prying action model, because that really didn't have much to do with the problem, so I don't want to get that confused. Okay. So we calculated the tensile force and the shear force, but then we also said let's compute the tensile force per bolt, the shear force per bolt. Okay, so we got 18 kips per bolt in tension, 13.5 kips per bolt in shear. So what are we going to do with that? Well, I want to look up some capacities. So let's look at a couple things. Start off, what's our bolt diameter? 3/4. Okay. Now, are we for this connection, are we experiencing a scenario of single shear or double shear? Single shear. Okay. And then our group, are we group A, group B, N, X, what are we? AX. Okay, group AX. Okay. So if this is the case, what I want you to do is this. Let's start off with shear. Okay, so I want to look up a phi RN, and just so I'm not confusing things, I want to look up a phi RN for the shear. So what is the phi RN in shear? That comes from table 7-1. Remember, we've got a group AX, 3/4 inch diameter, single shear situation. 22.5. Do I got a second on that? Okay, now that's 22.5 kips per bolt. Okay, now that is table 7-1. Okay, now that's phi RN for shear. Now let's look at phi RN for tension. Now when you look at that table, you're not going to see a delineation between threads included or threads excluded, and you're not going to see a difference between single shear or double shear, because none of that matters because there's no shear. Okay, so what is the phi RN for a 3/4 inch group A bolt in tension? 29.8. Do I have a second on that? All right. Okay, so I'll put table 7-2. All right. Everybody else able to find that? Okay. Now, like I said, we have 3 checks we've got to make. The shear, the tension, and the interaction. So let's look at the shear. The capacity per bolt is 22.5 kips per bolt. How much force is each bolt seeing in shear? 13.5. So it can hold up 22.5. It's only being subjected to 13.5. Are we good? Good. Tension. It can hold up 29.8. It's only subjected to 18. So we're good. Now, one thing I do want to point out, I'm being very diligent in the way I name things. Like, for instance, this is 54 kips, but this is 13.5 kips per bolt, right? This capacity that I looked up in this table is kips per bolt, kips per bolt. Does that make sense? So you want to make sure that you're being diligent when you label things. Like you don't want to compare this FRNV 22.5 kips per bolt to this, because that's the shear on the whole connection. You see what I mean? So just make sure you're being cognizant of how you're labeling things, because that matters and can cause confusion down the line. Sound good? Everybody okay with this? All right. Okay. Now, before we get into interaction, I do want to bring up something real quick, just so everybody's clear on something. I want to go back to this. So if you recall, the interaction curve that we're using is essentially this straight line, right? And remember, when we computed this straight line, or when we wrote the equation, we were essentially using this model right here. Remember how we said this is essentially y equals mx plus b, right? This is our y-intercept. This is x. And then this right here, that's our slope, right? So what we're trying to find is what is the effective tensile stress based on this line. So let's just go back to basics. If I want to find the y-coordinate on a line, go and find the x-coordinate, go up, and then there you go, right? So what I need is the x value. In other words, I need to know the shear stress on the connection. I take the shear stress on that connection, plug and chug into this equation, and it will tell me what is my effective tensile capacity. Does that make sense? Okay. So in order to do this interaction, this is how I'm going to go about this. All right, so we've got each of our individual components. Does everybody have everything over here? Okay. All right, so I'm going to go forward. This is example 11. Okay. Okay, example 11. So the first thing that we need to determine our interaction is our applied shear stress. Now, I know it's been a while since you all have had mechanics of deformable bodies, but even so, the fundamental equation for stress doesn't change. It's like pressure, a force over an area. Okay, so we're talking about bolts being subjected to shear stress. So samurai sword or lightsaber through a bolt, I need the area of that bolt. Okay, so let's look at a single bolt. Now, one bolt is 3/4 of an inch. So I propose that the area of a bolt pi over 4d squared, which is pi over 4 times 3/4 inches squared. What do we got? .442, bless you. Oh, 442. Now, how many of you still have table 7.1 or table 7.2 open? Look at the top, or look at the listing of each bolt, and it actually tells you what the area is, right? You didn't bring your manual, did you? But we're not in concrete, we're in steel. All right. Does everybody see that, though? You don't have to compute your areas. It's literally right there. So it's a neat little guide. Okay. Everybody with me? What's that? Well, I just wanted you to make sure you remember how to do this. And I also wanted to make another point. This is the area of a bolt. Okay, so this is inches squared per bolt. Okay? So if I want to determine the shear stress on this connection, I propose there's two ways to do it. Okay? The shear stress could be VU per bolt divided by the area of a bolt, or it could be the total shear divided by the total area of the bolts. Does that make sense? You can do it however you want, but make sure that you're being cognizant, okay? What I like to do is this. This is what I like to do. I like to say it's 13.5 kips per bolt divided by 0.42 inches squared per bolt. See what I mean? I like to literally have it stated that it's per bolt and per bolt because it's very easy to take, well, what is it, 54 kips? To take 54 kips divided by this and say, well, that's the shear stress. No, 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 no. That's not the total area. The total area is 4 times that, okay? So this is how I like to do it to ensure that I know I'm comparing apples to apples, okay? Everybody all right with that? What do we got? Say it again. 30.54. What are the units? So KSI. I got a second on that, Cal? All right. Everybody good so far? Okay, now, the next thing we need is we need a modified tensile capacity FNT prime. Now this is the one instance where we're actually going to have to go into Chapter J and look up some values. This is probably one of the few things we actually need to break out Chapter J. So this is what I want you to do. I want you to go to page 16.1-120. So all right, what we need is FNT and FNV. Now we can actually look this up in table 7-1. The problem is table 7-1 already has them adjusted by feet, by the resistance factor, and it's actually easier for this calc to just have the raw values. So let's start off with tensile capacity. Are we dealing with group A bolts or group B bolts? Group A. Now, does the tensile capacity by itself matter, or is it affected by whether or not the threads are included or excluded? No, and you can see it right there in the table, right? Didn't bring yours either. See, I called somebody else out. Where's yours? Well, it didn't work. All right. FNT, what is FNT going to be for a Group A bolt? 90. Does everybody see that? Okay, now, FNV. Now that changes, right? That changes whether or not the threads are excluded or not. Are the threads excluded from the shear plane? Yes, they're Group AX bolts. And if you have a Group AX bolt, what is the nominal shear capacity? 68. So I propose that we have 90 and 68 KSI, respectively. Now, here's the thing. So FNT, this is the nominal tensile stress that a bolt can hold up. But that is the nominal tensile stress that a bolt can hold up assuming there's no shear. But that's not the case for these connections because there's a boatload of shear on it. So what we're going to compute is a modified tensile stress, an FNT prime, that's going to be smaller than this based on the presence of FRV, the shear stress on the connection. So I propose that that formula is as follows. Now, here's the thing. Now, here's the thing. Here's the thing. I'm going to steal that from you. You're going to be graduated and long gone. I'm stealing that one too. Oh, these jokes are riveting, I'm telling you. All right. Back to some FNT primes. Okay, So I propose that FNT prime is computed as taking the minimum, a bolt load, 1.3 FNT minus FNT divided by phi FNV times FRV or FNT. Now, the reason for the minimum here is to account for the possibility that you don't meet that 30% requirement. In other words, if you've got 72 kips of shear and only 5 kips of tension, you go through and do this math and you won't see an effect. But that obviously isn't the case for what we're dealing with. The FRV, it stands for required, and honestly, I'll say this, I actually am not the biggest fan of that notation. I'm using the notation directly from the manual. The reason why the manual does things like FRV is because that's the manual's way of trying to write one equation that works for both LRFD and ASD. But for me, I would call it FVU or something like that. But I'm trying to use directly the notation that the manual uses to try and reduce some of the confusion. Right. But that's a good question. But it stands for required. So, because that's the required amount of shear that the connection has to hold up because it's there. Make sense? That's a good question. All right. So, bless you. We have the minimum of 1.3 times 90 KSI minus 90 KSI over 0.75 times 68, right? Times, what was FRV? 30.54? For these, yes, yes. Anytime we're talking about bolt failure mechanisms, it's 0.75, except for slip, which slip is a service condition, so we take phi to be 1. And then minimum of all that stuff up top, 90 KSI. Equals the minimum of something in 90. So I'm going to make y'all do the math. .1, or what, like 0.07, something like that? 0.10. Oh, okay. Wow. Why do I have 0.07? Wrong. Oh, not to get political, but is this like an alternative stress? Come on, that just presented itself. What are you doing? What are you doing? Oh, goodness. This is recording, too. Goodness gracious. All right. Is everybody okay with this number, though? Okay. One of the things I do really want to point out, though, is look at the value, okay? By itself, a bolt can, we're saying that a group A bolt can hold up 90 KSI in stress, but what I'm saying is because of the presence of that shear stress, you can't get that 100% of that tensile capacity. In fact, we can only reach 63.11. So we're computing a reduced tensile capacity because of the presence of shear. And think about it like this. If we had more shear, this number would go down. Make sense? Okay. Now, what I propose that we then need to compute is the following. Now, first off, do I have all of this? Okay. Is we need to compute a modified tensile capacity. What? No. We computed a, I'll tell you what, let me do this. Modified tensile stress to delineate. That one I will accept as we'll no, we're at like 3.5.
They said 3.5 like 2 weeks ago.
Well, that was 2 weeks ago. There's an expiration date. Didn't I tell you all that? Goodness. Now, what we're computing is this. We're computing a phi RN. But let me also be clear on something. The key word in this statement right here, bless you, the key word is this, tensile. And I'll explain why here in a second. Now first off, phi RN is just going to be phi times FNT prime times AB. Okay, so that is, bless you, that is a phi of 0.75. That is an FNT prime of 63.11 KSI. And then we have an area of what? What was the area of the bolt? Yeah, it's A sub B. I'm sorry, is that 0.442? Now, hold on, watch what I'm going to do. Inches squared per bolt. All right. Now, when you compute all that, tell me what you get. 20.92. Do I have a second on that? Okay, 20.92 kips. Now hold on, kips per bolt. All right, so that's important. Okay, be diligent on this because it's really easy to compare the wrong numbers. Okay, so regardless of what we compare this to, it's got to be one of the per bolt numbers, right? You know, kips per bolt. You know, what have you. The important word is right here, again, modified tensile capacity. So I propose we compare this tensile capacity against the tensile load. So in other words, we are comparing this to T sub U per bolt. And what is T sub U per bolt? There we go. So what does this mean? We're good. We just did that. No, that's a good question, but let me go back here. I mean, we looked at this right here because we've got, remember we did 3 checks. We've got the individual tensile capacity, the individual shear capacity, and then the interaction. See, look, here's the shear per bolt, here's the shear capacity per bolt. So we did do that.
Okay, so that modified tensile capacity is the interaction.
Yes. Yes.
So that shear and tension? I mean, we didn't do a modified shear capacity.
That's a great question. That's a great question. All right. The answer to that question is this. Okay. When we do an interaction check, what we've done is we have computed. Let me. Actually, what am I doing? Shift. Okay. What we're doing is this. Is we're saying, all right. Now hold on. Watch this. We are saying, based on some shear stress, we're saying, all right, let's go up and find out what this point is on the line. The way that we formulated that is we've said, based on a given shear stress, what is the required tensile capacity? We could just as easily say, well, the flip side, based on a tensile stress, what is the required shear capacity? There's actually nothing magical to say, well, based on the shear stress, we did the tensile capacity. It'd been just as fine to do the flip side. We don't need to do both because what we're ultimately after is this point on the line. Whether you go on the x-axis and go up or go on the y-axis and go over, you're still finding the same point on the line. That is a great question, though. That's a great point. Did that answer that? So you could very easily, let's put it like this. The equation of this line is y equals mx plus b, right? You could very easily reformulate that equation and say, well, it's x equals something times y plus something. It's still the same line, though. That answer your question? That's a great question. You had something, though, too, didn't you? Oh. In fact, I'm not sure if I have it. Do I have it actually in the slideshow? Right here. Okay, right here. If you look right here. So also note that the equations can be rewritten as to find a nominal shear stress as a function of the required tensile stress. That's basically the way of saying there's nothing special about trying to find an FNT prime. We could have just have easily found an FNV prime. But that's a great point. Yes? I'd add more bolts or space it out further. I mean, basically. I honestly, when you and the design procedure for a connection like this, there's no like shortcut way of doing it, so it's really just Excel. Set up a spreadsheet. Let's say you got 2 bolts. What's the shear stress? What's the tensile stress? Does it work? If not, add 2 more, add 2 more, add 2 more. The reason why I'm adding 2 more and not adding 1 more is because look at the geometry. You know, I've got a WT shape, so I want the same amount of bolts on one side that I do on the other. So that's why I'm using an even number of bolts for this iteration. But try 2. If that doesn't work, try 4. If that doesn't work, try 6. If that doesn't work, try 8. And that's where Excel comes into play.
How does defining loading affect things like block shear?
Actually, it helps it a little bit because you're going to have less shear. Yeah, or you're going to have, actually, no, let me say that backward. You're going to have less tensile stress because you've got some of that shear. So in many cases, it helps it. There are many instances, though, where combined loading hurts it. And the biggest instance is a beam column because columns are in compression, and things in compression like to buckle. And if you take a column that's already in compression and you add some moment to it, well, that's more compression on one side, so that makes it worse. So beam columns, it's sort of it really is, it's not very advantageous. That's why when you look at moment frames in buildings, the columns are bigger for that very reason, because that additional moment doesn't help the column out at all.
So would you just take the component in one direction to analyze block shear?
Yeah. Exactly. You just take that shear component. Well, in this case, it would be the shear component because you want the force acting on that connection in this fashion. These are good questions. Oh, we still got a few more minutes. We only got 13 minutes because we are going to end early. So, any other questions? Well, now it's 12, so yeah, too late. Now. Oh, you engineers with your math tricks. All right. Let's spend a little bit of time talking about some welds, and then we'll call it. So, I'm curious, how many of you have welded before? All right, I have too. I suck at it. I'll be the first person to admit. What I can do is get piece of metal A to be attached to piece of metal B. I can make that happen. Now, whether or not you get a nice, pretty, bead of weld with no porosity or anything like that, well, we'll have that discussion another day. But I can make my own. But the point I'm making is installing a bolt versus installing a weld. It's not the same story. Okay. Welds, I'll just go and say, welding is an art. It takes a long time to develop the necessary skill to weld. Okay? It takes a long time, and what?
Why?
What's that?
Why?
Because
Put some fire on it. Make it work.
no,
I think you might be the only person here that's wondering.
what's that?
I think Dean might be the only
Look, well, first off, I mean,
sticks to the labs. It's fun.
all right, welding. All right, first up, you've got all these, you've got all this protective gear on. You've got a welding helmet that you can barely see out of. Then you have to make sure that you're using the right consumable for the right grade of steel. You have to make sure that you're using the right heat input based on the given thicknesses, and you have to maintain your speed and consistency with your weld, and then it has to be inspected and pass qualification. So it's not like a bolt where there's the hole, there's the bolt. Like that's it. I mean, you have to go through significant training in order to do appropriate weld. I mean, you have to be certified as a welder. It's a learned process. Not really, no. I mean, you just have to, as long as your inspector is okay with the connections, it's good. I mean, you can be trained to properly install bolts in about 15 or 20 minutes. I mean, it's not that big of a deal. But welding is a learned skill. It takes a long time to master. Let's see. I'm going to show you all a funny video before it ends, just to relax you all a little bit for the concrete exam. But I do want to mention a couple general parameters. So welding, a lot of what we do from a design standpoint is derived from AWS, from the American Welding Society. We are not going to use D1.1, but D1.1 is one of the most consulted specifications on earth. It is the structural welding code for steel. And a lot of what we do and a lot of the design provisions that we do basically come directly from AWS. If you are a fabricator or you work for a fabricator or you work for anybody that does any type of metal fabrication, there's going to be a copy of D1.1 somewhere, guaranteed, okay? Because it is, in the world of welding, it is the authority. It is what we go off of. So it's worth mentioning. I do want to go through at least some of the fundamental processes for welding and some of the welding joints, and then we'll maybe show a funny video at the end. So some of these you probably never heard of, but when you start to see the conventional names, I think you'll get the idea, like shielded metal arc welding versus gas metal arc welding, flux cord, submerged. Some of this you probably never heard of, but you will when you start to get into it. For instance, shielded metal arc welding, you probably have heard of that as stick welding, right? How many people have heard of stick welding? Okay, that's a little more common, and it's called stick welding because for lack of a better term, you essentially have a weld electrode, which looks like a stick that's hooked up to, looks like a jumper cable. You feed an electrode through it. You have the other end of your welding machine attached to the specimen that you're welding. Once you touch, there's the circuit completed, and you start welding. When you complete that circuit, what happens is that electricity starts flowing through the electrode, and I mean, you're talking about a lot of heat input. So what happens is the weld electrode starts to get consumed, and you essentially create a big molten pool of steel. So you've got part A, part B, and the electrode all getting melted together. Once it cools down, you've got a welded joint, and that's essentially how welding works. I mean, you are not gluing together piece of steel A and piece of steel B. You are melting three individual components to create a common joint. Yeah.
Why you gotta use electricity?
Well, electricity will complete the circuit and then cause melting and sparks and fire. So it's just Gorilla Tape.
Hey, that stuff means business.
All right. Yeah, we don't use Gorilla Tape. One of the things I do want to mention is about the electrode itself, and this is a general commonality among welding in general. If you've ever seen the stick, if you will, the electrode that's used for welding, you probably get an idea of what it looks like. You have a metal core inside, but it's kind of covered by this granular, gritty stuff. You know what I'm talking about? Well, that stuff is, I mean, it's a very precisely controlled flux coating. The idea is as you melt it, right there around the connection where the action is happening, where everything's melted together, this coating also vaporizes and forms sort of a gas shield, and that sort of eliminates a lot of the oxygen and specifically the hydrogen in the atmosphere. Hydrogen is an enemy of welding. You don't want hydrogen anywhere around a welded joint, because what will happen is you can get hydrogen embrittlement inside the weld, and hydrogen embrittlement is bad because that makes a brittle weld. Brittle welds crack. We don't like that to happen. Okay? Sound good?
Is that what happened with the Henry?
What? No. No. All right. No.
The blimp that blew up from my,
They weren't welding.
It wasn't like, I mean, I'll be honest, it wasn't taking off, and they were like, hold on, we got to fix it. All right. One other thing that I think is worth mentioning, or one other procedure, is MIG welding. How many of you have heard of MIG welding? Now, the difference between stick welding and MIG welding is that you have electrode being fed through a continuous feeder. Now, you still have to have that gaseous shield, so you can get that through one of two fashions. I mean, if you have a large-scale MIG welder in a fab shop, you'll notice there's a big tank of gas that goes along with it. That's essentially your shield that will protect the region around the weld from hydrogen embrittlement. I personally always found it a little easier to do MIG welding than stick welding because for me, it was, with MIG welding, all you had to do was maintain your speed horizontally because the wire was being continuously fed. But with stick welding, you have to sort of go down because as you're going to the left and right, the wire is being consumed, so you have to go down as well. I always found that a little more difficult. I've also spoken to a lot of welders who thought MIG welding was more difficult. That's just me. With MIG welding, you're either getting that shielding gas that is protecting the joint from hydrogen embrittlement, or you're using a particular type of wire. If you ever have a cheaper, like Lincoln Electric, and it doesn't have the gas, you just use that special electrode. That electrode has that flux that'll protect the joint. You can always tell when you've used one of those flux cord wires, when after you've welded, it has that sort of white cloudy soot on the joint. That's when they use that flux cord wire to protect the joint. Everybody good so far? Want something kind of funny before the concrete exam? Okay, all right. I'm going to skip ahead a little bit because I kind of want to show you something. All right. One of the things that will matter to, now you all get a kick out of this, one of the things that matters later on when we start talking about welding is the direction at which we load a joint. This would be a longitudinal weld where the welds are sort of being loaded in shear. This is a transverse weld where the welds are loaded in tension. Please do not load a weld transversely, okay? Transverse welds behave very poorly when it comes to fatigue. And if you don't believe me, I have a video which might help illustrate it. It might take a little while to load, but as it's loading, I'll tell you a little bit about the, I see that. Let's see. They changed their website a little bit. The guy who is giving this this presentation is a guy named Dwayne Miller, who's the director of research for Lincoln Electric, so he does know welding. So, let's see, AISC on demand webinars. Let's try this. Not live webinars. Continuing education. Education archive. Let me zoom out a little bit so I can see what's going on. Because I know it's 2012. I know. They just redid their website, so bear with me. Yes, it is. I might have to hold this off till after the exam. I don't want to do that. Oh, I skipped one. Well, I hit search and it just didn't work. There's no like typing it in. I'd love there to be, but come on. Wait. Oh, here we go. Here we go. Oh, no. Hold on. Oh, that'll be bad. Oh, wait. Hold on. I'll try this and then we'll call it. I think I showed it last year, so. What's that? No, I'm not. Oh. Oh, yes, we did. Yes. Okay, so this is a presentation of, this is a presentation of what happens when you weld transversely. This is talking about a particular McDonald's in Oklahoma. So,
a restaurant over the freeway, and you walk up these steps to go to the restaurant. Now, I go there every year because my in-laws live here in Dallas, and I'm in Cleveland. My folks are in Kansas City. And so we get in the van and we drive down to Texas. We spend a week here in Dallas, and then we drive up to Kansas City, and Vanita is right about the time we need to get an ice cream cone. And so we go up these steps to go get our ice cream. Now, there's the restaurant that straddles the freeway. It used to be called a Glass House. I throw this in for free. You don't have to pay for that. That was owned by Howard Johnson's. They still retain this name, Glass House. Here's the steps that you're going to go up. Now, my oldest daughter, Rachel, she had just gotten a digital camera for Christmas. And I said, Rachel, go in, go get your camera. And she said, why? And I said, just go get your camera. She said, why, Dad? I said, honey, get your camera. I want to take some pictures. She said, of what? I said, I want to take some pictures of welds. She said, Dad, nobody cares about welds but you. I said, no, people are going to love these welds. This is great. They're going to love these, and I'm going to show them to my seminars because they're going to love these welds. And you can see they've cracked, see? And depending on when they catch the cracks, you see they've been repaired a different number of times, see? So if this one cracks, then that one cracks, but if they repair these, then that one doesn't need to be cracked, see? And so I thought, this is fascinating, and they've cracked all over, and they've been re-welded. And it's aluminum, Charlie, it's not steel. And so now what's going on here? There's the handrail, and the kids run down with their ice cream, and they swing on this lateral loading, and there's the weld between the vertical and this piece of material down below. And it kind of looks like the weld on the end of a cover plate, doesn't it? Kind of. And that's a category E detail. And category E details crack at the weld toe, and this cracks at the weld toe. So then they repair welding. And so they repair it, and now what fatigue category do they have? Well, it still kind of looks like a cover plate, and they crack at the end of the weld, so they crack at the end of the weld. All right, so then they repair it, and now what do they have? Well, it kind of looks like the end of a cover plate, and it cracks at the end of the cover plate, so it cracks at the end of the weld. Now, you think they're never going to solve this problem, but you're wrong. When the repair welds get up to the handrail, this is going to be solved, okay? And I'm going to be there. I'm going to be there when the welds finally get up to the handrail. So it's just a matter of time, and we'll keep doing this. Now, I've been monitoring this since 2006. And in 2006, the door is open, okay, and there's a ladder in here. I went back in 2008. Actually, I went back in 2007 as well. Now the door's closed, and you can see that they've actually lost a couple of these verticals, and these are gone now. Okay, that was in 2008. And so I went back in 2000, that's 2008, those are missing. I went back in 2009, and they really solved the problem. They solved the problem. If you notice, they have a wet floor sign over here now in 2009, and I was so disappointed. I thought the story's all over, but it's really not, because I want you to look over here on the right-hand side. Now, this is only a few months ago when I was there in 2011. The door is really getting to be pretty ragged now. It's not in very good shape. In 2006, you notice these three berries of spatter here? And this screw kind of goes from 1 o'clock to 7 o'clock, okay? Now that's in 2006, and you can see that these welds are intact in 2006, but by 2009, there's the spatter, there's the screw, and number 4 and number 5 have now cracked in that far right-hand rail in 2009. I went back in 2011. There's still the 3 berries of spatter, and 3, 4, and 5 are cracked. In fact, if you go all the way up, you can see that 6 has cracked, 7 has cracked, there's 5 has cracked. And so this thing is now, another rail is going through the same kind of problem. But by the time we get up to 8 and 9, those are no longer cracked in 2011. So I dug back at the old data and tried to make a comparison. I've got good data from 2011. You notice that 7 of them are cracked in 2011. When I go back to 6, I know that 3 and 4 and 5 are not cracked in 2006. By 2009, I have some fractures. So now we can start plotting this data, and the research is ongoing, and I'll be back next year, and we'll talk about what's progressing there. All right.
All right. We're done. See y'all in concrete.